All right, our first speaker of the day is Nikhil Raghuram from Virginia Tech, and he's going to tell us about vanishing orders and U1 charges in F-theory. Take it away, Nikhil.
Great. Thank you so much, Cody. And thanks so much for the organizers for the chance to speak here. This has been a great series of talks, and I'm looking forward to seeing it continue in the future, I guess. All right, so the work I'm going to be talking about today is done in conjunction with Andrew Turner. And really, this is work in progress, by the way. And it ties into a few themes which have been fairly common in the F-theory literature so far. And these are questions about sort of which massless spectra can occur in F-theory vacua. Questions like what types of gauge groups or which representations of light-charged matter. I should say that for today, I'm pretty much talking about massless spectra. So whenever I say something like spectra or charged spectra, I really mean massless spectra. And of course, there's a question of how these particular massless spectra are realized in F-theory. And these questions are important for a few reasons. From a physics perspective, this is a good way to explore the F-theory landscape in swampland, essentially asking the question, which consistent supergravity spectra can be realized in F-theory? And exploring these sort of questions can lead to new constraints or new string constructions, things of that sort. And this is a good way of probing these physics questions. And from a mathematics perspective, many of the physical properties of F-theory models are encoded in geometry. So if you can understand the physics of F-theory, that can also give you lots of insights into the mathematical properties of things like elliptic fibrations and Calabi-Yau manifolds, things like that. So there are many interesting aspects of these questions that are that involve the area of U1s in F-theory. These are questions like, what sorts of U1 charges can massless matter have in F-theory? What combinations and what charge spectra? This is interesting for quite a few reasons. One thing I want to highlight is that there's currently been proposals that there's an infinite swampland of charge spectra based on this work by Taylor and Turner. Essentially what they've done is they've shown that there's infinite families of models that are consistent with the anomaly cancellation conditions, where the charges can be arbitrarily high. It's known that many of these, or infinite number of these, have to be in a swampland, but it's not known which of these models can be realized in F-theory and really what the physics principles are in terms of which can be realized and which can't be. So because of that, it's worth just better understanding how massless U1 charges in F-theory work. In particular, what are the geometric features of F-theory models realizing different charges? And that takes me to the very more specific questions that I'll be talking about today. Basically things like, can we make general statements about how different charges are realized in F-theory? And another question is, how can one determine U1 charges without performing a resolution? So to maybe give more perspective on these sort of questions, it's good to review some basic aspects of F-theory and U1s in F-theory. This probably is common knowledge. With F-theory, the basic idea is that you describe a model using an elliptically fibered Calabi-Yau manifold. And part of the reason why U1s are particularly interesting in F-theory is that they occur through a slightly different mechanism than the nonabelian gauge algebras most people are familiar with. So there's a pretty standard story with nonabelian gauge algebras that they're associated with divisors or codimension 1 loci in the base with singular elliptic fibers. And the different singularity types correspond to different gauge algebras. And at codimension 2, you can have loci where the singularity type enhances, and that supports charged matter. And you can determine the non-abelian representation by looking at the enhanced singularity type and determine the representation that way. I'll describe this in more detail in a bit. But there are also U1 algebras, which come from or associated with extra rational sections of the elliptic fibration. In these instances, charged matter will still occur at codimension 2 loci where the singularity types enhance, but the U1 charge is actually determined by the behavior of the section in these cases. So to describe these ideas in more detail, there's a standard story about non-abelian gauge algebras where you have these, as I mentioned, you have these singular fibers along codimension 1 loci, and after resolving singularities in your elliptic fibration, the elliptic fibers along some of these codimension 1 or codimension 2 loci could have the shape of ADE diagrams. So I've illustrated this here for an A4 and A5 kind of diagram at codimension 1 and codimension 2. We can essentially determine the gauge algebra and the matter representations from this resolution. So at codimension 1, if you have a dual M-theory picture of your F-theory model, you can think of wrapping M2 branes on these extra components that appear, and these will give you sort of the roots of the gauge algebra. There's complications involving monodromy for non-simply laced algebras, which are not going to be too important here. And charge matter kind of occurs in a similar way. You'll notice that at codimension 2, you get an enhanced diagram, and there's sort of extra components that appear, and wrapping M2 branes on these extra components will give you the weights of charged matter. But it turns out that at least at a heuristic level, you can often determine much of this information without having to do a resolution. So let's focus on a model in Weierstrass form, which I've written here, where the discriminant delta is 4f cubed plus 27g squared. And there's this well-known thing called the Kodaira table, which relates different singularity types to the vanishing orders of f and g and delta. And of course, associated with these singularity types, there's a bunch of algebras. And so what this means is that you can often read off singularity types and the nonabelian gauge algebra by looking at the orders of vanishing of f and g and delta. And there's also simple rules to test for monodromy to distinguish between these multiple algebras that are listed. Again, those won't be too important for what I'm talking about today. But the point is that you can often look at the orders of vanishing of f, g, and delta and usually figure out the gauge group. There's kind of a similar story with charged matter, even though it's a bit more heuristic. So there's this thing called the Catswaffle method that lets you determine oftentimes the non-abelian charged matter representations. Essentially, if you have this enhanced singularity at codimension 2, you can determine the gauge algebras associated with the codimension 1 singularities and the codimension 2 singularities, and break the adjoint of that enhanced gauge group into reps of G. And you can read off what the charged matter is based on the decomposition of the adjoint of H into the representations of G. And at least at a heuristic level, you can often determine G and the enhanced singularity H from the orders of vanishing of F and G and delta. Now, I should say that, strictly speaking, that Kodaira classification that I mentioned only holds in codimension 1, but you can often get away with using it at codimension 2. You have to be a bit careful, but you can often get away with doing that. And so at a practical level, this means you can oftentimes, at least heuristically, determine the non-abelian matter representations without having to perform a resolution. And this can often, in practice, be easier than performing a resolution and figuring out the matter content that way. So as I mentioned, U1s sort of occur through a somewhat different mechanism, and in that they come from extra rational sections of the elliptic vibration. So in all our models, we'll assume that there's at least one section. We'll call it the zero section. But in the models we're talking about today, because we are interested in U1s, there'll be more than one section, even an infinite number of sections. And these sections form a finitely generated group under an operation known as elliptic curve addition. So this is oftentimes known as the Mordell-Weil group, which will take the form z to the r plus g, where here g is this finite torsion subgroup. And for today's purposes, it won't be too important, so you can kind of ignore it. This number, integer r, is known as the Mordell-Weil rank. And you can work with the physics of what happened in the situation. You can find that the resulting gauge algebra is U1 to the R. And roughly each U1 is sort of associated with a generating section, which generates one of the Z's in some sense. So charged matter in these situations, you'll still have codimension 2 loci with some enhanced singularity, and wrapping M2 branes on extra components still gives matter, just as before. But in this case, the U1 charge is actually determined by the behavior of the section. So the specific equation is given by Q is given by the intersection of the sigma of S with C. So here S is a generating section. Sigma is something known as the Scioto map. It's a homomorphism from the group of sections to the Néron severity group, essentially giving you a divisor for a section. And C is this extra component I was talking about that supports the matter. And so what you can do is you can look at the resolved geometry, look at the behavior of the section, and figure out what the charge is. So I've illustrated this for two cases here, for charge 1/5 and charge -4/5 in a thing with SE5 fundamentals. And you'll notice that the ADE fiber type is the same, but the behavior of the section is somewhat different. So here, the section is intersecting one of the components transversely, and in the other case, the -4/5 case, the section is wrapping one of the components. So the different behaviors of the section are giving you different types of charges. So you can now try and go back and see how this fits into kind of the Weierstrass models I was talking about previously. So let's suppose we want, just for now, focus on a U1 gauge algebra, just have our Mordove group be Z. So we need a generating section that generates that Z. And so what we're going to do is we're going to ascribe S by some components X hat, Y hat, and Z hat, which solve the equation above. So X, Y, and Z will be expressions that depend on your base coordinates, or more properly, sections of line bundles on the base. In principle, they can be rational, but you'll notice that there's this rescaling here. So oftentimes what you can do is you can just scale away the denominators and remove shared factors and get into a form where the X, Y, and Z are essentially holomorphic. It's also going to be convenient to define this W hat, which is 3x hat squared plus F Z hat to the fourth. So with this story, you can ask, is there something like a Catswaffle method for U1 charges where you don't have to do too much work resolution-wise. You can look at the orders of vanishing of something and figure out what the charges are. But as you might be able to guess, using only the orders of FG and delta, you're not really able to do that. And that boils down to sort of the fact that you have similar ADE fibers regardless of the charge. For example, if you take singlets, which are uncharged under nonabelian gauge group, they'll vanish the same orders at their codimension 2 loci, regardless of the charge, whether you have charge 1 or charge 2. It's always occurring at I2 loci. So that's not going to work. But what if we look at section components? So this is a program which was sort of started in this work. So it was previously observed that for charged singlets, these are things charged only under U1, not under an abelian gauge, not under a non-abelian gauge algebra. That the orders of vanishing of the second components are correlated with the charge. And in fact, the algebraic structure of the Weierstrass models in these cases are closely associated with these orders of vanishing in a very subtle way. So you can list out what the orders of vanishing are for Z, X, Y, and W, these section components, what they were according to previous models in the literature. And then you can ask, is this part a more general pattern? And if this was more part of a more general pattern, you could say that maybe we could use this pattern to just look at the section components and read off what the U1 charges are. The challenge is that it is tough to construct F3 models with larger charges, and basically with 4 data points, it's kind of tough to make any general statements. But there is a slight trick you can do, and this was sort of first pointed out in the Morrison Park paper. You can start with a U1 model just having charge 1 matter. So I listed the Weierstrass model here, and here's the generating section for the U1. And this locus F12 hat and F9 equals 0. There are I2 fibers with extra component C. This is what's supporting the charge 1 matter. And if you look at the generating section, it satisfies sigma of S dot C is equal to 1, where sigma is a Schrödinger map. So that gives you charge 1 matter. But it's important to note that there's also sections NS generated from S by elliptic curve addition for any integer n. And sigma is a homomorphism. So if we try and find the charge-like thing for ns, that is sigma of ns dot c, you'll find that it's equal to n. So in some way, at f12 equals f9 equals 0, the section ns is behaving in a way that looks like it admits charge n. So what you can say is, okay, I'm going to look at these ns sections and look at the orders of vanishing at that locus f12 hat equals f9 equals 0. And you can do this for n equals 1 to 4, and you actually recover the orders of vanishing that appear in the previous model. So that gives you a sense that what you're doing here actually gives you things that hold more generally. So you can go to orders to n equals 5, 6, 7, 8, and look at the numbers. And if you stare at this enough, you can find a pattern that the ord z for these guys is given by this formula right here. And the ord x, y, and w is going to be 234 times ord z plus 0, 1, 1 times n mod 2. And you would expect that in a generating section for a model that actually has q equals n matter, the generating section components will vanish to the same orders. Okay, so you can ask why this pattern. I won't have too much time to go into this, but there are very similar numbers appearing for evaluations of elliptic divisibility sequences for p-adic elliptic curves. I won't have too much time to go into this, but it's a very interesting connection, and there seem to be a lot of parallels here. But another question that you could ask if similar patterns hold in other situations, that is, what if matter is charged under both a U1 and some non-abelian gauge algebra? So you can play the same game and use the higher section in the model with a G plus U1 gauge algebra and see what you get. So before I do that, it's probably worth talking a little bit more about the charge units and how this works when they're non-abelian gauge algebras. So to go into more detail about what the Schrödinger map does, if you expand out the expression for the Schrödinger map and dotted with C, you'll find that Q is given by this formula here, where S is sort of the homology class of the section, and C, as before, is this extra curve at codimension 2 supporting the matter. These alpha I are basically, they're curves in the singular fibers supporting the simple roots of G, and T are the divisors found by fibering those over the codimension 1 locus in question for the non-abelian gauge algebra. And C inverse here is the inverse Cartan matrix for G. So if you look at this formula, it appears that you can have sort of a fractional U1 charge. I mean that most of these terms involve intersections, which are inherently integers, but you have this inverse Cartan matrix here, and that will have fractional entries. And so you can basically have non-trivial fractional contributions when you have this S dot alpha I be non-trivial. Singlets will still have integer charges, but if you have an alpha I, that is like you have a non-abelian gauge algebra, then you can have these fractional U1 charges. And so essentially, which fractional charges you can have is sort of controlled by which of the alpha I are hit by the section. And so this is a codimension 1 phenomenon, and this is related to the global structure of the gauge group. A lot of these ideas are described in more detail in this paper, so I would highly recommend reading that if you want to learn more about this. But the punchline is that you can have fractional charges for things that are simultaneously charged under a non-abelian gauge algebra. So as I said before, is you start using the higher sections in a model with a G plus U1 gauge algebra. As before, if you have a generating section satisfying sigma S dot C equals Q, where Q can now maybe be fractional, and a codimension 2 locus, then these NS sections are going to have a charge-like thing that be NQ. So we're going to just find the orders of vanishing for the NS sections, and you're going to expect that for models with genuine NQ, the generating section is going to vanish to these same orders. So we've done this exercise for simply laced non-abelian algebras with various generic reps. So between all the different gauge groups and representations we've looked at, it's about 550 sets of orders of vanishing numbers. And remarkably, with all of these, there's a pattern. So as before, we're going to consider a model with a G plus U1 algebra where G is simply laced. There's some codimension 1 locus where the singularity type is G. So I'm being a bit sloppy and referring to the singularity types by their universal covering groups associated with them, which are simply laced. And for singlets, you can take G to be SU1. And you can have matter at a codimension 2 locus where the singularity type enhances to H, where again, I'm referring to singularity types by their by a group. And then you can look at the orders of vanishing. So, and these are given by these formulas at codimension 1 along the locus supporting the gauge algebra, and at codimension 2, which is the locus supporting the matter. So just to work through some of the notation here, I and J are integers ranging from 0 to the rank of G or the rank of H. And you can roughly think of this as referring to the component in the resolved fiber hit by the section. More so at codimension 1. At codimension 2, it gets a bit trickier because there's wrapping and things like that. But so now these tau g, these are triplets of integers, which there's particular expressions for them which depend on the group G or H in question. I'll give you an example for SUN in just a bit. DJ are the number of elements, it's an integer giving the number of the elements in the center of G. And C inverse G II is the ith diagonal entry of the inverse Cartan matrix. Or if I is equal to 0, we take this to be 0. And of course, Q is the U1 charge. So we to make these things more specific, let's say we have a SUN gauge algebra at codimension 1. I can range from 0 to n minus 1. Tau is given by this triplet here, where UN is the minimum of I and n minus I. This is the value for the inverse Cartan matrix, and D, which is the number of elements of the center, is n. And if you're looking at fundamentals, the enhanced algebra you see at codimension 2 is essentially SU n plus 1. So, I mean, I've talked about deriving these expressions in terms of looking at these higher sections, but you can ask whether this actually holds in previous models in the literature. And we've looked through at least some of them, and it seems to actually work in quite a variety of them, whether it's, I mentioned sort of the Morrison-Park form, the toric hypersurface models involving U1s, we've checked that seems to work there. I already mentioned this model, a lot of the SU5 cross U1, SO10 cross U1, E6 cross U1, E7 cross U1 models, and this work, and the SU5 cross U1 squared and SU4 cross U1 squared in this work, it seems to work, at least in these models. These are the ones that we've checked and they had previous spectra given. And whenever we've used these models to derive the charge spectra in a case where we didn't have the previous spectrum, the results have agreed with anomaly cancellation. So this suggests that these formulas do work in somewhat more generality. And if you could really develop this in more detail and really solidify this, this gives a potential few benefits. One is that this would give a way to easily kind of read off the charges, at least up to sign, without having to perform a resolution. The other thing is that, as this was sort of a formula that is kind of for general charges, so if it does hold more broadly, this could be used for exploring the F-theory landscape and swampland. I mean, if you wanted to find a model with some kind of arbitrarily high charge, this could give you a sense of what the geometric criteria are for such a model. And it gives you something to aim for if you're trying to construct it. You might be able to see whether you construct it, whether something goes wrong, if you try to have these orders of vanishing, something like that. So I wanted to give you an example of how to do this first thing before I go. So let's look at an example from, this is an example from the previous literature from Kunstler and Shaver-Namaki. Here's the Weierstrass model. You don't have to worry too much about the details of this. All you have to know is that there's an SU5 on sigma equals 0 and a U1, and here's the generating section. And according to the work they did there, they showed there was a fundamental matter with charge 6/5 at this locus sigma equals B00 equals 0 with an SU5 to SU6 enhancement. And if you look at the orders of vanishing of the section components, at codimension 1, these are given by 0, 1, 0, 1, and at the codimension 2 locus, these are given by 2, 3, 1, 4. Okay, so let's try and see whether our formulas sort of reproduce the charge in this example. So let's first look at the codimension 1 behavior. We expect it to be given by tau of SU5 of I, which the formula says is given by 0, 1, 1 times the minimum of I and 5 minus I. And the model says that this is given by 0, 1, 1. So you can read off that I is either 1 or 4. And if you plug into our expression for the inverse Cartan matrix elements, you would get that this is equal to 4/5. So you have this piece of data. Now you can go to codimension 2, where the singularity type is sort of SU6. You can first look at X, Y, and W, the orders of vanishing in codimension 2. You'll find that it's 0, 0, 0. And if you compare that to tau of SU6, the expression sort of given here, you would find that J is 0. And you can take this inverse Cartan matrix element to be 0. And I already mentioned that d of sun is n, and the inverse Cartan matrix you get from codimension 1 is 4/5. So if you plug all this stuff in, you get this expression 5/12 q squared plus 4 over 10. 4 over 10 should equal the codimension 2 order vanishing of z, which happens to be 1. And if you solve for q, you find that the absolute value of q is 6/5, as was previously seen in this model. So that demonstrates how one might use this to read off the charges. There's a whole bunch of aspects that I haven't been able to mention today. As I sort of alluded to, these different formulas work for other simply laced gauge algebras. There's a natural extension, there's multiple U1s. There's a slight generalization of these formulas that work for bifundamentals. And as I sort of mentioned, there's connections to elliptic divisibility sequences for p-adic valuations. So just to conclude, the summary of this seems to be that the information about U1 charges seems to be encoded in the orders of vanishing of the section components. So a bunch of future directions that there's, to understand this more rigorously, basically extending this to different types of algebras and different types of representations. And if there's similar sort of formulas that can appear for other descriptions of elliptic vibrations. And with that, I didn't have anything else to say, so thanks.
All right, Nikhil, thanks for the very nice talk. We can use our clap emoji to indicate so. Our first question is from Gary.
Hi, very nice talk. I asked Wati this question yesterday in a different seminar, but I think I can also ask you too. So you talk about the charges, but I was always curious how one would go about normalize the UN current in F theory, because what's physically observable is the charge times the coupling. And so for non-abelian groups, the normalization of the UN current is fixed by the structure constants, but you don't have the luxuries for U1. And so this gives you the flexibility of normalizing your gauge coupling that's realizing the U1 at a higher Cat-Moody level. And so I wonder if you can see how this would come about in F theory. And in particular, the realization of the U1 at a higher Cat-Moody level is one way to get rid of the exotic fractional charge states. So it may be interesting to look into this in F theory as well.
Sure, and that's a good question. I'm not sure if I have anything too useful or intelligent to say. I guess so the gauge coupling in these F theory models is sort of controlled by something known as the height of the section, which I didn't have too much time to go into, but that will give you sort of a divisor in the base, and the volume of that is kind of corresponding to the coupling for the U1. So that kind of gives you some sense of how that sort of normalization would work. I think it's a good question, and unfortunately I don't have too much useful to say, but I mean, I would be happy to try and think about it more and offline.
Right. So from that point of view, you could have different U1 factors with different normalization. Is that what you are saying just now?
Yeah, and this sort of gets to, this may be partially related to the fact that you have these higher sections for which, if you calculate the height of these higher sections, they'll scale by, if you have a section n times s, they'll scale as like n squared or something like that. So it might be related to that, but I don't. I want to think more about this before.
Okay, thank you. Thank you.
Okay, I think Ling raised his hand next. Ling.
Yeah, thank you. Hi, Nikhil. Thanks for the great talk. Can I ask about these codimension 1 formula that are so basically which components in codimension 1 are intersected by the sections? Is that something known already from theories of elliptic surfaces? Because I would have assumed that this is something that you would already observe, for example, for DP9s or K3s and etc.
Oh, so to be specific, you mean the formulas for the?
So right. So if you the formulas, for example, the tau vector that you have there, which
sure.
Right, so from essentially from the vanishing orders of the section coordinates to infer from that the component in codimension 1 that's been intersected by the section.
Yeah, so we observe these taus based on the what I mentioned earlier, which is looking at the higher sections and or the NS sections and finding their orders of vanishing. It could very well be that these are previously known in the literature. That certainly could be the case. I've tried looking at it. I haven't found anything quite like this, but I've only looked in sort of a limited way. So it could certainly be that this is in the literature somewhere previously. I haven't found where, but if someone knew, that would be very useful to know. But I guess, yeah, so to sort of answer your question in brief, I don't know if these were in the previous literature, but they could very well be.
Okay, maybe I don't know if you have tried that or looked it up. But maybe one cross-check would be if this formula, for example, also holds for torsional sections, which has nothing to do with like charges, but
yeah, it's a good question. Yeah, it's a good question. We haven't looked at torsional sections yet, but it's a good suggestion.
Okay,
thanks.
Cool, thank you.
And our next question is from Howie.
Hi, nice talk. Thank you very much. I was just wondering whether your formulas can say anything if there's an upper bound on Q, like excluding some infinite families of U1s.
That's a good question. I think these formulas wouldn't. So I should say you can use these
consistency that you would see.
Yeah. So that's a good question. And so I guess in some sense these formulas probably wouldn't give a bound in that. Even though I've written it in terms of Q, these are really describing the sigma.c that I mentioned for some section, which may not be a generating section. And I mean, and you can see in F theory, there are higher sections which do have these sigma.c arbitrarily large. That doesn't mean there's actually infinitely large charge in some sense. So from a matter spectrum kind of perspective, the question that you're sort of interested in is that in units where the GCD of the charges is 1 or something like that, what's the highest charge? Which is in this more geometric language would be something like, what is the sigma.c for a generating section? And these formulas, they would work for a generating section, but they also work for sort of one of these higher sections, these NS kind of sections that I mentioned. So I guess the short answer is that this alone wouldn't give you an upper bound, but it might be used in conjunction with, you could say maybe in certain models what the geometric properties might be, and you'd have to probably use the full spectrum of the model, like saying not just the highest charge, but what the other charges are. But you could use some of this geometric information to maybe glean something about what the limits are. But I think these formulas alone wouldn't give you a bound.
Do you geometrically know if it's even finite? Maybe not give you an upper bound, but whether it is finite.
So I guess sort of the point is, I guess that if you're just sort of looking locally at the singularity, you can have something that looks like arbitrarily high charge. I guess the key question is whether the section is a generating section, which is a very kind of subtle problem. It's a more global problem about space rather than what's kind of going on locally. And these formulas are only about describing what's going on locally in terms of the behavior of the section. So, I mean, I absolutely agree. It would be great to have a bound come about some way. I think these formulas alone won't give you a bound, but they could be used in conjunction with other things to potentially do that.
Okay, in the interest of time, we better keep moving despite all the great discussion. Nikhil, thanks again for the excellent talk.
Should I stop share?
Yes, please.